dance vibration today. So hopefully everyone can start working on the homework. So here is a summary of what we done on the introduction of dance vibrations. And if we focus on the steady state response, and in particular on the magnitude, steady state response magnitude, then that is the form here, okay? And this magnitude really doesn't matter. The response is due to cosine or sine. But the phase angle is a little bit different. So refer to our lecture notes. So starting based upon here, we begin to look at the curve. And so if we divide the magnitude of the steady state response with the static diffraction, so basically this one, again, this one defined as the magnification factors. Okay, so basically that is the definition of the words. And this one we've seen last time and in the damped vibrations. So for this one, for the damped vibrations we have is this 1 minus r squared, and I simply copy from this slides. Okay, so again, R is our ratio of the frequencies, the working frequency respect to the undamped natural frequencies. Okay, and zeta is the damping ratio. So if you would say for this case, for damping ratio equal to 0, then this one will be simplified into 1 and then 1 minus r squared, and let me take the absolute value here, okay? Basically this one, after the setting the damping ratio equal to 0, you can see this form basically is what we mentioned in our undamped vibrations, and this term you exercise in the previous homework, right? And in the previous homework, we come up with a solution that come up with a negative value of this one. And I said in that hint, I said put a negative sign away into the face. So in this way, then we take the absolute value. So here, I just want to let you know, and here is a little bit extension to what we have learned. And we look at the curve on the magnification factors. Depends on the damping, and we have a different. And when damping equal to 0, basically that is converting into the undamped vibrations. However, if you remember our undamped vibrations, and we have the curve is something like this. So that's an R, and this is 1, and capital F theta. And this one, if you remember, our formula is 1 minus r squared, okay? So in our drawing of the curve is something like this. We have a negative term here. We have the values and become negative in certain range, okay? And look at this curve here. For this one, you see everything simply flips into the positive range, even including the zeta equal to 0. Simply, if you compare corresponding to zeta equal to 0, this curve is basically identical to this one. But for this case, again, you keep in mind, they simply flip this negative curve onto here. Then you use the dashed line to representing is the flipped counterpart, okay? And by flipping into here, then how can we deal with the negative term here? Basically, showing in here is we add in additional graph called the phase angle. So the difference between here is this. In reality, in this portion, we know the value is negative. Put into this graph, we simply convert into everything positive. So we have to deal with negative, considering this negative as at 180 degrees. into this phase diagram. Okay, so that case would be something like here. Okay, so phase diagram here, I cannot see that very clearly, but that is the meaning of what we mean here. So basically, the older phase, we consider older phase, all the negative sign being can be taken care of in this phase diagram. Okay, so in summary, the conclusion is this: in this phase, we simply take all the value as a positive, as an absolute value here. Okay, so if you see from this moment onward, you shouldn't feel kind of weird. How come like this? Simply we take all the things positive absolute value in this the magnification factors. Okay, so once we and now the other features, when damping ratio equal to 0, then we know the maximum value basically go to infinity. Okay, in theory, and that is happens when we add the omega equal to omega n at the resonance. On the other side, if we have a damping ratio, no matter how big or how small it is, then the maximum value becomes finite. Okay, basically you can see here, if we have a damping ratio, basically this number in the square root will become a finite number even for r equal to 1. Okay, so that is another features you have to see here. Okay. And another one is when damping ratio is greater than a certain threshold, then the curve becomes like this, and something like this, or something like this. And for example, for the two illustrated curve, basically the saying is they are monotonically decreasing. So that means for such curve, they don't have a peak. And that happens when the damping ratio is greater than certain value. And how big is that value, then I'm going to show you. Okay, so that means saying before we get into the more detailed the numbers or formula, you have to some kind of the concept in mind. If you if you're going to design a system with damping, and there's two scenarios you're going to face. The first one is if you select a damping is small enough, and then you should expect your system have a chance to have a peak. So that means have the maximum value. And that maximum value basically is greater than 1. The peak is greater than 1. So that means the dynamic, the magnitude of steady state response will be always greater than the static diffraction. For the first case you design, that means the damping ratio is small enough. Okay, that's the first case. The second case is if you would choose your damping ratio large enough, then you wouldn't see any peak. So that means you should expect the maximum, the steady state response will have a maximum magnitude that is smaller than the static diffraction. So here in kind of two scenarios provide us the kind of design considerations. Whether you want to maximize the system's vibrations or whether you want to minimize the system vibrations. If you want to minimize the system vibrations, you better to have the damping ratio large enough to suppress this maximum magnitude. Okay? So basically the two cases and depends on your applications. And then later I will give you, right now I want to give you more information, more quantitative. So here, let me take notes here. So keep those kind of the schematic features in mind, then we can have more information. And so let me put the note onto the curves. The first one is when damping ratio increase, then we expect the magnification factors will keep decreasing. Okay, so so I would say the maximum of this magnitude, the maximum of the damping ratio will be 0. So I would say the maximum of this magnitude will be 0. So I would say the maximum of this magnitude will be 0. So I would say the maximum of this magnitude will be 0. So I would say the maximum of this magnitude will be 0. So I would say the maximum of this magnitude will be 0. So I would say the maximum of this magnitude will be 0. So I would say the maximum of this magnitude will be 0. So I would say the maximum of this magnitude will be 0. So I would say the maximum of this magnitude will be 0. So I would say the maximum of this magnitude will be 0. So I would say the maximum of this magnitude will be 0. So I would say the maximum of this magnitude will be 0. So I would say the maximum of this magnitude will be 0. So I would say the maximum of this magnitude will be 0. So I would say the maximum of this magnitude will be 0. So I would say the maximum of this magnitude will be 0. So I would say the maximum of this magnitude will be 0. So I would say the maximum of this magn will be decreasing. Okay. And the second one is the maximum So the second note tell us is for undamped systems, we expect the maximum, the peak, happen at the resonance. However, if we have a damping in the system, then this relation tell us is the maximum magnitude happened not at R equal to 1, not at resonance, and at a little bit off from the resonance. And what is that values? Okay, so basically these approximations, this is the true value here. So maybe the better way is, sorry, how about this? Let me replace this one. Okay, so that's what I mean here. So when we have a damping, then the maximum value is occurred at a little bit of from the resonance. So why we have such value here? Okay, so this basically, I think this is the one of the piece of the formula. I think you need to box and you might use it. Okay, basically this telling, that information telling is this. So for example, for zeta equal to 0.2, the peak is here. Okay. The peak is, if you look at here, that for the zeta equal to 0.2, the peak is here. And that one is a little bit off from R here, so corresponding, that one happened at here. Okay, so that one happened at R is not equal to 1, a little bit smaller than 1. And exactly how to calculate this one basically R is equal to plugging into our formula 1 minus 2 times zeta squared, 2 times 0.2 squared. For this one, this case is this. So you simply calculate it while you can determine where the peak over happens there. Okay. So here I want to explain to you why we have this formula. The derivations is this, and we know we look at our original formula. We have this one, 1 minus R squared and plus 2R zeta squared. We have this formula for describing the magnification factors. Okay, so if we're looking for if we are looking for the maximum value of these numbers, so which means we're looking for, you see this number is 1 divided by something. So if we're looking for 1 divided by something and the maximum, that means we're looking for the minimum of the denominators. So we're looking for is 1 minus R squared plus 2 zeta R squared. We're looking for minimum of this number here. Right? Equivalent. So in this way, basically this problem becoming is to find the value of R to minimize this function, piece of cake. We're simply using is if we given a function of r, we're looking for the minimum value. Basically, the technique is this. We simply take the derivative with respect to r of this at equal to 0. From here, we're finding r value equal to certain r star, and that is the value to minimize or maximize these functions. Okay, and then we apply the differential equation or calculus to check whether that corresponding is the maximum or minimum. And for this case, it's the minimum. So basically here for this case, we simply take the derivative of 1 minus r squared plus 2r zeta squared. We set up this one equal to 0, we solve for r. And then in this way, the r, you should be able to find it. And that will be equal to, and yeah. So that will be equal to r, will be equal to this one. Okay. So here you skip a few steps, you can proceed. So for this case, then we can even determine, now we have the r star, the minimum happened at this one. So that means we can determine the value, the maximum will be equal to, that value happened at at this value here. So you simply plug in r equal to this value into that calculation, then you will get that number will be equal to 1 to zeta, 1 minus 2 zeta squared. So from here we can tell is this, the maximum value. So I think this is the information, so you can box it. So that means the peak of the magnification factors occurred at this particular R value, and the magnitude of that peak equal to this one. Okay, so which means, let me graphically showing here. So if we have the magnification factors here, and this is capital X delta ST, so let me draw a curve here. Okay, so for this one corresponding to has a damping ratio, corresponding is a damping ratio, and this is a value of 1. So from here you can see that corresponding is when R equal to 1 minus 2 zeta squared, okay? And then the peak value equal to 1 to zeta times 1 minus 2 zeta squared. So that is the meaning of that box equations. I think this will be useful and for your applications, because most of the time when we design the systems, we always concerned is how do we suppress the vibrations, or on the other side, how do we magnify, get the maximum outcomes of certain vibrations. Okay, so for example, if you go to the machine shop and new machine shop, I think they spend quite a bit of time to set up the machine. And that step, to my knowledge, I talked to Eric, and including the mounting the pad to the supporting legs, and from between the machine and the ground. And one of the purpose, if you have time and they want to simply is to two purposes. One is to isolate or suppress the ground vibrations, which is rare in Alaska, maybe 40 years a time, earthquake 7.2 degrees, but that is very rare. Most of the time, they want to suppress the machine's vibrations to the ground. Okay, when, for example, CNC machine when to operate, you can see that machine sometimes vibrates quite a bit. Okay, depends on how they operate. Okay, so that's one case. The other case, if you have used the accelerometers, accelerometer is some kind of the sensors, and the size of the sensor usually not bigger than my thumb, okay? And that is a small sensors mounting into somewhere and to measure the accelerations of some object. So for that case, they must be sensitive enough to detect something. And that's a typical, kind of reminds me, and that's a typical mechanical accelerometers sensors. Cell phone, inside the cell phone, we have a chips there, and one of such chip is called the sensor, motion sensors. The motion sensor basically, you see, once you change the orientations, the screen will be changed accordingly, because there's such sensors inside there that detect such a motion change, and that is again, they're using is a three-dimensional XYZ accelerometers there. And that kind of sensors are fabricated by the silicon-based fabrication. Basically, they're using MEMS, the micro MEMS, micro-electrical MEMS, micro-electrical mechanical systems. Okay, so they have a such sensors. So those sensors, they want to amplify the signal. They want to have the sensitive detection of the motion. So in this way, usually they try to go to the more sensitive. That means they choose the system have the higher this kind of magnification values here. Okay, so that's a kind of the two examples, and so I would say in practical applications, this graph will be more useful than once we have done all the calculation in mathematics, and that is more practical usage. So I would say this graph is more important than the fundamental mathematics. Okay. So that's given to this one, and the third one is this. And for the third one, we know that when R equal to 1, in particular, if we operate a system at its resonance frequencies, okay, which means we operate the system when omega equal to omega n, that means we choose our working frequency at the resonance frequencies here, then we see what happens. Then under these situations, this value basically, we plug in R equal to 1 and equal to this equation that's simply equal to this one. So at the resonance frequencies, the system magnitude is exactly equal to this number. So usually we use the damping ratio as the index to tell us how big the magnitude this could be. This value is not the maximum, but this value is very, very close to the maximum. Okay, good? If you want to be accurate, then you simply use this one. If you want to approximate, this is good enough. Good? Okay. Any questions? Without we have this.